Okay, so for the positive definite test, positive definite test, I don't know how to spell it. Definiteness, I don't know. Test, we say that for any, let's say, vector such as this, it must be greater than or equal to 0 for x for all Rn, which we can call this, I don't know, this will declare the dimension, I guess. Example, R of 1 would be like 1D, R of 2, 2 dimensions, x and y. That's what I mean. So, if we declare x, then x times x summation, y will get replaced by x, and xi, yi, it'll be x squared I. And we see that when we declare this, that x will declare that 0 for all real numbers will be positive. So it is positive definite. And if you were to do the same thing for y, it would be the same. Same for, I don't know why it's not writing, y comma y, right? You can say that this, you're just declaring, you compare x with itself. It's basically what this is doing. Or you could do it with y. Or if you were to do it with z with z, you would get 0 because z is not a variable. It's not part of this, which would also prove that it would be equal to 0, which would still make this test valid. Okay. So for this one, we're doing conjugate. Conjugate symmetry. Symmetry. I don't even know if I spelled that right. Symmetry. I don't want to keep this word. Didn't write it well. Okay. So basically, for conjugate symmetry, if we flip the order of the dot product this here, if our result is different, then it fails the test for this dot product of vectors to be an inner product of R sub R Rn. Okay. So basically, if we flip x dot y equal to y dot x, if this is true, then it passes the test, right? So what does that look like? Basically, let's say they were vectors. We'll do an easy one. Let's say x is 1, 1, 1,
and y, and y is, I don't know, 2, 1, right? Product is you just multiply them. 1 times 2 is 2, plus 1 times 2 is 2, plus 1 times 1 is 1. You're just multiplying these together and then adding them all up. Obviously, if we flip that order, right, if we put y times x, this one would be up top and x would be on the bottom. It wouldn't change the value, so the order will not change the scalar. What is scalar? It's basically the dot product of the result of the dot product between two vectors, which is basically like the length of the vector itself. Okay. And it passes the test, obviously. So yeah.
So now the third test is checking linearity, right? And then for this test, basically, to sum it up in a set of words, we need to take each vector, right, x dot y, what we're given. And if you're ever confused about this right side, this is basically the same thing as x dot y. The summation of x and y of each, part of the vector is basically the same thing as doing the dot product. Good to remember that this is actually equal to the dot product, the summation. If you have a summation and two variables in there, you could rewrite it as x dot y. Anyways, I know the expression already says that, but when you check linearity, basically we have vectors x and y, right? And we need to take each vector separately. We're going to focus on them separately for this first step. We'll do it in step 1.
Let's see how this
Need to multiply each one.
goes.
We'll say a and b. These are scalars. A times x plus b and y. So first we must multiply each vector separately, here and here, by a scalar, and then add them together, and we'll get a new vector. And then we need to do the dot product with z. Okay. Now let's see how that does over here. So we have the summation n is equal to 1. And then let's do the same thing. We have a x I, right, plus b y I, right? And then we're going to multiply it by z of I. Why z of I, not the dot product? We're just multiplying. It's not a dot product. Why? So let's look at it in steps, not steps. Let's look at it in parts. This is a vector, right? That will result in a vector. This will result in a vector. This is its own vector, right? Because multiplying by a scalar, right, and then adding that together will result in a new vector. You're going to take the dot product of that vector with z. Okay, so remember how I said you could rewrite this? Well, let's say to replace this with something called a new variable called ci, zi, right? this whole expression was replaced with ci. Well, like I said, summation of two variables, vectors, um, can be replaced with as such. And then, let me actually write the declaration down. AXI plus BYI CI, right? And then we plug it back in. CI is equal to, when you convert it to the dot product, that little I goes away, right? And C would be equal to AX plus BY. But you see what I'm trying to say here. Hopefully. Hopefully. That you can replace this variable here, we'll declare it as one vector, and then replace the summation with the dot product between the two. Basically what you're doing. And now that you see these are equal, right, they're the same on both sides, except that's supposed to be B. This proves linearity. Good. Slash passes. Okay. Alright, so this is part B. And we need to find the positive definiteness of to see if this is a valid inner product. And it's good to know that you should remember this, and that this will be a complex uh, function, like you're dealing with complex vectors. And how you know that is you see this conjugate here, right? You're not dealing with a real inner product. You'll be dealing with a complex one versus a real one. And that is what this formula is going to be used for. But without knowing that, right? If you see this conjugate here, it typically means that we're asking for the complex conjugate of the function. Anyways, let's see if we can determine if this is positive definiteness, if it's valid for the first test. So I rewrote it since we're comparing x with itself. It's good to note that when you have something like this, x of t times the conjugate version of itself, complex conjugate, you'll end up with this, something like this. And obviously we can see that that will only produce positive numbers greater than or equal to 0, which would pass the test. And if you want to check, right, say we have complex number a1 plus 3j, the conjugate version would be 1 minus 3j, right? And if you multiply these, say you want to integrate from 0 to 1, you'll get 1 minus 3j. Hold on. I don't know why I'm confused. Um, yeah. And then you'll get plus 3j, and then minus 9j squared. These will cancel. 1 plus 9, because j squared is equal to -1, I'll get 10. Positive number. Integrate 10t from 10 minus 0. It's positive. We're good. All right. So that's just to prove that it ended up being positive, even though the conjugate of something you would think means the opposite. You would think you might get negative, but you're good. I actually need that for my work. But T0, T1. Okay, now let's prove symmetry. Symmetry. What's symmetry again? Before I do, let me write this. Positive definiteness. Okay, and we're going to redo this over here. Good page. Okay, so we're going to prove that this is conjugate symmetrical. So if we reverse the order, right? And what we're proving is this statement here, that these are equal. So first, let us reverse the statement and the expression, where x takes place where y is, and where y takes place where x is, like so. This will be the conjugate now, but then we need to take the conjugate of said thing, which will just apply it into here. So that'll be equal to which is in fact equal to which is also equal to the original equation. As you can see, it's the same thing. It doesn't matter the order in which you multiply. So it is conjugate symmetrical would be the word, I guess. All right, and for the third one, linearity. Let me copy down the equation. All right, so since the audio for part 2 wasn't enabled, I have to do this again. So I'll break this into steps. So for part 2, it says compute the following for the vectors. V is equal to R3. Well, we're going to go in detail a little for R. You know how in the previous problems it mentions, why is it erasing? R of n declares the amount of dimensions for the vector specifically. X, Y, Z. Notice how there's 3 for X and Y. That's because R is set to 3. We're in 3D space. We can go to 4, 5, 6, 7, 8, 9, 10D. That's why when we're doing the ones up here, right, where does it say it? Where does it say? Anyways, when you're doing the inner product, right, of something, you're comparing it to something like R of n, which is, let's say, all the dimensions, whatever, right? That's what you're comparing the inner product to using these tests. And when you use these tests, then you can determine if it is a proper inner product. Now going back to here, R of n declares the dimension, and then we have x and y. Right? And we're doing these three calculations, which are pretty straightforward. Dot product, magnitude, and then we're squaring them, and then we're projecting. Right? There's a formula for projecting, and I won't ramble for that one. It's pretty straightforward. Let's see, 3, no, no, no. Don't pay attention to my work. I know I did the problem already. That was because I lost signal with my headphones, I think. Okay, so we'll do the dot product first. Good thing to note is, why are you saying? Good for you, I guess. For the dot product, right? The rule is do x dot y, right? Two vectors, dot product. What's happening is we're multiplying. Let's see, how do I want to do this? The size of these vectors is 3, right? We have the first term here, second term, and the third term, right? We multiply each vector's first terms together, their second terms together, and then their third terms, like I have them like pointed like this so that you can kind of see that. There's no arrow, but you see what I mean, hopefully. So one, I want to do a dot because we just did the dot product. I will do a little x times 0. Actually, no, we'll do it like this. Plus, plus, yeah, plus. Dot product produces a scalar, right? That's a good thing to know. -2 plus -2 times 3. Okay, and we'll get, let's see, the resultant of this is -6, -2, and the last one 0. So we'll get -8, or -6 plus -2, which is -8. Right. And the order in which you multiply it, see, for the second part it says y dot x. Well, it doesn't matter which, if you change the order. If, say, well, when you're doing y dot x, you're moving the 0 and the 1, and -2, and this 1, and the 3, and the -2. You'll still get the same answer. So, like so. That's how you do the dot product. Hopefully, that makes sense. And then the next part, what was that? Oh, it turned off. We're doing, don't look at my work. I have to redo this. We should get those answers though that you saw. So for this question, we grab the magnitude and then we square it. The y, the magnitude of it, and then we square it. So something we know about the magnitude, right? We're going to take each term inside this vector. 1, 2, and third term. Square them and then add them all up and then square root them. So it's going to be something like this. What happened? Oh, it looks to restart with me. Hold on, let me get back to that point. And then we're going to take 1 squared plus 1 squared plus -2 squared and square root it. And for this one, we're going to take 0 squared plus -2 squared plus 3 squared and square root it. Notice that there's a square outside of that, like so. That's going to make that square root disappear. So we can ignore that square root. Right. So we'll get, this will be 4 plus 1 plus 1, which is 6. This will be 9 plus 4 plus 0. 9 plus 4 is 13. Those are your two answers for B. Straightforward. Now let's do C, projections. All right. Erase that. Not worried about all that. These are your formulas you need to know for projecting. Let's not look at that. We'll get back. We'll get to that answer. Past me did that. Okay. So we have this formula, and you can see when we project y onto x, we have y we do x dot y times y and then y dot y on the bottom, right? So it's key to know the one you're projecting onto, y onto x onto it. X will be, so it's easy to remember, you'll have x in the corner, and then you're basically replacing everything else that's the thing you're trying to put onto said vector. You're projecting y onto x, it'll be all y. But if you're projecting x onto y, then you swap them, like so. Just a good formula to remember. It isn't, it's pretty, not bad to remember. You're just swapping the variables when you're projecting the other, when you switch what you're projecting. Anyways, x dot y. Okay, we actually did that earlier, but we can do it again. So I'll do this in my head. No, I won't. I'll do 1 times, I'm being slow. Oh, x dot y. We'll just pull it from back up here. Oh, it's gone because of whatever I did. That's great. X dot y is going to be 1 times 0, which is 1, plus 1 times -2, which is -2, plus, I don't know why I did that, that's wrong. 1 times 0 is 0. And -2 times 3 is -6. So we'll have -8 up top. Projection of yx, -8. On the bottom, we're projecting y, or we're doing the dot product of y with itself. We're going to have 0 times 0, which is 0, -2 times -2, which is 4, plus 9. You get 13 times y. Well, what is y? Y is a vector. So we're going to do 0, -2, and 3. This is your projection. Okay. So what you're doing is you're taking these dot products, right? That's going to produce a scalar that you're going to be applying to vector, for this one, x, right? And you'll multiply this out to 0, -2, and 3, and that'll be a new vector, right? So we'll do the other one. Projecting x onto y. Okay? And x is, use the formula we have here. Remember, we're just swapping them all around. So y dot x, we already did that one. It won't change. It's going to be -8 up top. Why is it saving? -8 up top, right? Divided by, it's going to be y dot y, which is going to be 0 squared. No, it's going to be x dot x, my bad. It's going to be 1 squared plus 1 squared plus -2 squared, which is going to be 1 plus 1 plus 4, which is 6, right? And that's going to be times the vector y, which is 0, -2, 3. No, vector x. What am I doing? Vector x, 1, 1, -2. Ta-da. Have that scalar can be multiplied in all of these. You don't have to, well, you can leave it out. You know the result is, that's your answer. Okay, so now we're going to do 3. Let's talk about 3. 3 is evaluate the following inner product of functions. So we need to find the inner product of functions on these inner products on the left on these intervals from 0 to 2 pi, which I forgot how to do. Take a quick break. Oh, oops. how to do that. And we have the inner products that we're evaluating from here, right? From the period 0 to 2 pi. So we're going to be integrating the inner product over 0 to 2 pi. Why do we choose integral? A standard inner product is given by the formula G conjugate of t like this is equal to the integral from point A to B of f of t G conjugate of t dt, right? So that's why we're integrating. And don't worry about the conjugate here because we're not dealing with a complex number. We're dealing with sine and cosine. So we don't have to worry about the conjugate. So we're plugging in basically the inner product and we are going to integrate. So how would we integrate this? Well, we know if we integrate over a full period of cosine and sine by its orthogonality, this would definitely equal 0. But we're going to do a little more proof than that. We're going to use, what is it called? Use a little trigonometry. I'm going to say 1/2, right, sine of n plus m times, hold on, n plus m, writing t. Dude, I hate how plus signs always look like t. And integral. Then we have plus sine of n minus m t dt. Now let's integrate. So we're going to have, how do we get sine? A positive sine function. We want negative cosine, right? And we do a u sub inside. We're going to have 1 over n plus m. Put the negative up there. N plus m t. We're going to have another minus over here. Created? Why did I say? Oh yeah, because we're integrating sine. Okay, never mind. I'm confusing myself. 1 over n minus m cosine of n minus m t dt. Evaluate these from 0 to 2 pi. And at 2 pi, it's going to be 1. And then at 0, it's also going to be 1. So we're going to have the same functions, right, canceling each other out. So we're going to have, let's say, let this be x. This is going to be equal to x. Essentially, we're going to have x minus x, which is going to equal 0. We're going to have the same case over here. So we're going to say cosine of 2 pi, well, let's just solve it. So we know that's just going to be which is equal to 0. They're the same point, but they're not, you can't say they're exactly equal. But the easier way to evaluate this would be if you typically, let's say we have uh, a cosine function, right? Cosine, 1, boom, boom. A full period is 0 to 2 pi. So if we go from 0 to 2 pi, from point here to, let's say this is 2 pi, right? The area here and here, the area cancels out. Set it equal to 0. So by orthog, how do I spell that? Orthogonality or farnality? I don't know. Equal to 0. You could say the same thing from the beginning. If you integrate anything, cosine or sine function from 0 to 2 pi, you're going to get 0 as a result. Because the area under the curve will result in 0. All right, so for our other case, I'm just going to start over. We're going to start over for this one. I know I was briefly explaining. So for this case, this is different, right? Because n and m, right? You have when n is not equal to m, right? And in that case, we will have, let's see, when they are not equal, right? They are separate. It's not a good way to explain it. When n is not equal to m, you cannot combine the two sine functions, right? So in that case, when you integrate these functions, the area will cancel out, and that will be equal to 0. But when you have them equal, sine of nt, I hope that did not pick that up, you have a special case. You have sine squared of nt. Well, you may think, well, this is still a sine function. You integrate it, blah, 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 0 to 2 pi. You're going to get 0. But if you do this conversion, right, you'll see, what is that equal to? 1 minus cosine of 2nt, right? Divided by 2. Well, if we integrate that, 1/2 gets away from that. And if you integrate this, we get t over 2, which is 2 pi, and the other one's going to be 0. We're going to ignore that one because it's 0, over 2, and we'll get pi. What? When you have this case, you will get pi. And so for part C, we have, we'll look at this case, and we have our formula, 0 to 2 pi, f of t, which is e to the j n t, conjugate of gt. It's going to be the e to the j m t. Now for this case, we will be grabbing the conjugate because this is a complex form, right? We have a j. We are complex. So let's put in our numbers. Here from 0 to 2 pi, e to the j n t times e to the negative j m t dt, right? Okay. So we need to look at those cases again. We have a case where they're equal and where n is not equal to m. So when they are equal, it'll be e to the j n t, e to the negative j n t. Okay? So exponentials. It'll be e, factor out the j and the t, it'll be n minus n, which is equal to 0, right? jt 0, and it'll just lead to 1 as your answer, and integrate that, you'll get t from 2 pi to 0, saving. You'll get that this, when n is equal to m, we'll get 2 pi, okay? Now when they are not equal, right, usually, if you find that one, when you look at it, you can figure out when n and m are equal, or if they're not equal, if you find one where you have a value, like 2 pi or whatever, the other one's probably going to be 0. But if we solve and they're not equal, e to the j n, we'll combine them already. j t n minus m dt, 0 to 2 pi. We'll integrate that. We'll get 1 over j n minus m e to the j t n minus m from 0 to 2 pi. And we'll focus on this part here. So we'll have e to the j 2 pi n minus m. And then we'll have minus e to the, it's just going to be 0, right, which will be 1. This on the left, right, what do we know about a complex number? It has a cosine variant of 2 pi n minus m and a sine variant. Is it plus? I have no idea. J sine of 2 pi n minus m. Well, we know sine at 2 pi is 0, but what is cosine? Cosine is going to be 1, right? It's going to be 1. So 1 minus 1 is equal to 0, and the whole thing will be 0. So when they are not equal, right? Yeah. When n is not equal to m, we get 0. Boom. You like it. So typically when n and m are equal, you will usually get a value back, but there are cases where that's not true. But for these, they're not too crazy once you look at them and understand how sine and cosine work.
Finally got this to work. Okay, so now we're on to question 4, which states we need to compute the what can I say? Trigonometric Fourier series for the signals in the figure. This being the figure, and we need to do, which one's E and F, I'm pretty sure? E and F, okay? So to compute E and F, we're using, before I go further, we can see that all these functions are periodic, right? And to compute periodic functions, we use this formula. I didn't draw it that great, but hopefully you can read it. A O, A N, and B N. If you want to break it up into parts, we need to solve for A O, B N, and let's not put B N first. Let's put A N and B N. Those three things are what we're going to solve for, right? And we must solve for the first three terms. Think of it as we're solving for a series, right? Power series. Um, Calc 2? Calc 2. And we need to solve for the first, well, not really the first three terms. The first term's here, right? We need to first find a0, an, and bn. Well, what is that when we're looking at the function? Well, what we're really solving is for, like when we do with power and energy for signals, we will be solving for 1 over the period integrated from, let's see, over the whole period, right? The period, if we look at it, it goes from, we're looking at e here, these ramp functions. It goes from 0 to 3, right? That's one whole period of that function. So we're integrating from 0 to 3, but, it wouldn't help to integrate where it's going to be 0 no matter what. So we're going to integrate from 0 to 1. Okay. And then as the function will be, we're going to say x of t dt, whatever that function is in between that interval, dt. And then we need to solve for the cosine and sine versions of uh, the function. That's how I'm going to word it. This being cosine and this will be sine, b. And depending on your function, if it's even or odd, you won't have to solve for both, right? Because if it's odd, you only you won't have cosine part of the function, and if it's even, you won't have sine part of this function. So to solve for an, it'll be 1 over, no, 2 over t, the period, right, integrated from where it matters, 0 to 1, x of t cosine of omega naught n times t dt, I believe. Okay. Yeah, that's right. And we, so yeah, this here is just the first a0 is for just the average of one period, right? Then an is cosine the even, bn the odd, right? And we need this 2 over t to count the negative and positive portions of cosine and sine, because we need to get the proper, amplitude of both portions. So it'll always be 2 over t, the period. And then we have 2 over t not integral 0 to 1 x of t sine of omega naught n t. And something else that's important, what is omega naught? Omega naught is equal to 2 pi over the period. That's it. So now let's solve these equations. So first, let's solve for a of 0. So 1 over, well, what's the period of this function? Well, to get from one point to another, that's the same. You go from 0 to 3. So period of 3, integral. What's the integral of just x of t? What is x of t even? X of t is what the function we're integrating under. And for this ramp function, right, it has a slope of, if you want to integrate under this triangle here, it goes from 0 to 1. If you want to capture what's under there, that touches the axis, the slope's just 1. So it would just be t. 1 over 1 being the slope, but it's just t. And dt from 0 to 1, you could put like plus 0 to remember that you're integrating from 0 to 3, but the other portion is just 0, so it doesn't really matter. Integrate, you'll get t squared over 2. And you'll get 1/2 minus 0, which is it's just 1/2 times 1/3, 1/6. Alright, that's the first part solved. And that's 100% right. And then we got 8n. Okay, let's solve that. Let's bring this down here really quick. And this is what I have so far. I forgot to hit play while I was doing that. But simply, I've been integrating this and solving for it. Where did I leave off? I have no idea. But wherever I left off, I'm going to start from, let's see here. Alright, we're solving a sub n. Did I even, I hope I got this part. I think I got. I'll start from a sub n. Now we're doing the even function. We have the period on the bottom, which is this 3. 2 divided by 3. And then we have x of t here, multiplied by the n w naught times t. W naught is 2 pi over 3. And then we're going to do integration by parts. You can just double check with my work if you do this. And then we get to the bottom here. And it's important to evaluate, I forgot to evaluate this integral here from 1 to 0. And that'll be 3. Then we'll make this a positive here and reverse the order. And this is all multiplied by 2 over 3, the period. So come down here, and we can do nothing. I swear there was an option to like resize it? No? Well, it's all multiplied by 2/3. I don't want to rewrite it, but I will. Okay. Well, this would be equal to a of n. Now we need to solve for b of n. Alright, so now we have b sub n. We need to do the sine portion, the odd portion of the function, which is 2/3. Basically almost the same setup, but it's sine. Well, let's do integration by parts. U is equal to t dt. And we have dv is equal to sine 2 pi n over 3 t dt. Okay, and v would be, when we integrate this, it'll flip what's inside. 2 pi n times, if we want a positive sign, we need a negative cosine inside. No dt over here. Okay, now let's plug this in. uv is going to be negative 3t over 2 pi n cosine 2 pi n over 3t from 0 to 1. At 0, it would be 1 for that whole... Oh, no, it'd be a little different. I'll do that and complete that left side in a second. Then plus the integral from 0 to 1 of negative 3 2 pi n cosine 2 pi n dt. Now let's integrate the right side since that's the hard part. It'll flip what's inside that cosine, and the integral to get the integration of cosine. We're just looking at the cosine, forget the negative. Cosine is just sine. We'll get a sine back. Oh, excuse me. Alright, we'll get a sine back. So we'll get negative 9 over 4 pi squared and squared, because we multiplied by another one of those, sine of 2 pi n over 3t. Okay, from 0 to 1. Then we'll get sine at 0, nothing. We'll just get negative 9 over 4 pi squared n squared sine of 2 pi n over 3. That's it. T at 1. T is equal to 1 for that one. Minus, it would be 0. So we're just not worried about that one. Because sine at 0 is nothing. Okay. So cosine. Okay, let's plug in the numbers for cosine. We're going to get negative 3 at 1. If we plug in 0, t at 0 will make the whole function 0. So we're just going to get what it is at 1. Cosine of 2 pi n over 3. Now let's bring it together. Negative 3. And I don't like that negative next to that 9, so we're going to fix that. Never mind. Never mind. Never mind. I'm not actually going to fix it. Stop. Come on. Right. Let me write this out here too. It doesn't want to write at all. What the heck? You see how it's like not writing? Cosine. Okay. Minus 9 of 4 pi squared n squared. Okay. And that should be... Alright, and after checking my work for a good bit, this is the right answer. And I forgot to include the minus from u v minus the integral of dv duv minus duv. Because it goes as uv, my u is horrible, u times v minus the integral of du v du. That's integration by parts. And this should be b of n, at least I'm pretty sure. So the final answer for this question is just going to be all of these summed up together. So you're going to take a of n, which is just 1/6, but where's b of n? This is a of n. Or you could just write a0 plus a of n plus b of n plus dot 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 dot. That can be your answer. Because that's what you just solve for, what they're equal to. You're just using them as a substitution. Because it's too much to write it out. For me at least. I don't want to do it. Because you're solving for all the summations. So, now we need to do part F. Um, yeah, it's gonna be fun. Oh my god, I don't have enough time to do all that. Alright, part F. Okay, now to solve for our average portion, a0. I've set it up like this. Let's look at the ramp function. I set it up into this part, this portion, and I don't know what I was going to say. This portion, and this portion. Those three different parts need to be integrated under a curve, like so. And I have them set up, t plus 2, 1 for the unit step, and t plus 1. Whoa. I think this needs to be a minus 2, right? Yeah, my plus minus. There we go. Needs to be set up as the following. Okay. And this needs to be negative because this is a negative slope. Alright. Now we're good. And then we need to multiply all of this by the period, which is 1 over 6. Right? The function comes back every 6 seconds. 1 over 6. It's kind of messy, but let's solve it now. So if we integrate each one, t plus 2, let's do that one first. Okay, let's see. T plus 2. So we'll get t squared divided by 2 plus 2t. From negative 1 to negative 2. We'll get 1/2 minus 2 minus 2 minus 4. Hold on. Did I mess that up? Yeah. Yeah. Okay. 2 minus 4. Yeah. Okay. Um, I hope it's recording. Alright, it was recording, so we're good. Now, this comes out to be negative 2, positive. On F, cancel, cancel. 1/2 times 1/6 is 1/12 for the first term. Alright, so for our first integral, we got 1/12. Now for the next one, 1 we'll just get t if we integrate that. From 1 to negative 1. 1 plus 1 plus, we'll get 2. Yeah, from integration. 2. 2 times 1/6 is 1/3. And then t minus 1. T squared divided by 2 minus t from 2 to 1. I'll get a 4 over 2 minus 2 minus 1 half minus 1, negative 1 half, positive 1 half. So we'll get plus 1 half from that. Then we'll get 4 over 2, 3 over 2, negative 3 over 2, 4 over 2. We'll get 1 half times 1/6 is 1/12. I don't even know if my math is right. Hopefully it is. This can be 4 over 12. So we'll get 1 half in total as our A0. Okay, not bad. Now we need to, oh my, integrate 3 different portions. With cosine. Oh my, I don't want to do that. Okay, well, t over t naught, not write it over there, t over t naught. Integrated. I'm not very fond of integrating this much, but, integrate from, fuck, 0 to what? Or negative 2 to 1. Of t plus 2. Of cosine of n omega naught. What is omega naught? 2 pi over 6, which is pi over 3. Yeah. N t. That's so much integration by parts. No, you can't do this to me. This is actually brutal. Integral. Come on now. Don't do this to me. From 1 to 2 of, what is it, t plus 1? T minus 1. Okay. Alright, now we're going to let u equals t plus 2 dv equal to cosine of pi nt over 3 du is going to equal dt, and v will be 3 over pi n cosine of pi nt over 3, and not cosine, it'll be, to get the cosine, sine, just sine. Okay, and now we'll bring it down here. T plus 2, 3 pi n sine of pi nt over 3. From negative 2 to 1, negative 1, minus the integral of whatever this is. This is so long. I can't do this anymore. Okay. So to get sine, a positive sign will need a negative cosine. It's going to create a negative. It'll make it positive. we'll get 9 over pi squared n squared from this inside factor coming out. Okay, we'll evaluate this from -2 to -1. We'll do this one to the left first. So the first one's going to be -1. That's going to be 1. Okay, so it's going to be 3 pi n, because it makes a 1 from this in here, times sine of -pi n divided by 3. Then we got -2 on the bottom. Makes 0. Beautiful. We love 0. Means I don't have to do anything else. Alright. Alright. Now let's move on to the right side. We're going to get simplified from here. We're going to get 9 pi squared n squared cosine of -pi n over 3 minus 9 pi squared n squared cosine of -2 pi n over 3. Okay. Plus, bring this down. Okay, we have our first term. Woo! 2 more to go. Ah, this is painful. Okay. 2 more integrals. This hurts. What's my battery at? Okay, I need to charge this real quick. 1 second. Okay. Next integral is, let's see, cosine by itself, which is actually a fairly easy one. Cosine of what? Pi n t. Okay. And this is just going to be integrated. Whoops. 3 pi. Why do you keep doing that? Pi n sine of pi n t plugging in the values for t. I'm yeah. 3 pi n sine of negative pi n over 3. I feel like there's a trigonometric thing I could do there, but I don't want to. So that's our answer for that one. Now let's do the last one. Thank the Lord. T minus 1 cosine of pi nt from what? 1 to 2? Yeah. Yeah. So we're going to let u equal t minus 1 and dv
do du is equal to dt. V is going to be equal to 3 pi n sine of pi n t over 3. Now let's substitute that back in. uv on the left side minus the integral. I feel like my heart's stopping slowly. I don't know why. Of 3 pi n sine of pi n t of 3. Must be slight heartburn. I don't know what that is. 1 to 2. We must evaluate this from 1 to 2. At 1, let's make note on the left, we get 0. So we don't have to worry about 1. But 2 we do. We'll get 1 from here. We'll just worry about the inside of the function. 2 pi n. Okay, now let's I'm tweaking. Let me integrate the inside of this function. Please help me. So the integral, to get a positive sign, we need a negative cosine, so we're going to get a positive out here. We'll bring out we'll end up with like a 9 pi squared n squared cosine pi n t over 3. We need to evaluate this from 1 to 2. I sure hope we do. Then, I'd be so mad if like not a single thing was recording and I'd have to do most of this over again. I'd cry a little. I don't know if this is right, but it's better for you to see something, and when you're doing the math with me, you'll probably catch it, hopefully. 2, we'll plug in the boundaries. Yeah, they'll both exist, so there'll be 1 for 2 and 1. Okay. Plus, okay, and then we'll multiply this whole expression by what? What was it again? I actually finished 2 over 6, which is 1/3. What am I doing? Stop this. Okay. Multiply by 1/3. And where's this one? Multiply by 1/3. Okay, so now if we add all these up, we're chilling. So A0, we'll call this one A1. We'll call this one, I'm so lazy, A2. And we'll call this one, oh no, I missed one. Call this one A2. This one will be A3. So A0 plus A1 plus A2 plus A3 plus dot 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 is our answer. Also, B of n does not odd. This is an even function. no sine. Okay, so that, you can substitute what these are in. You know what? I'm just gonna write it out. I don't want to get points taken off. So we get 1/2 plus, it actually isn't that hard. I can just copy and paste. Let me do that. This one. Okay. Plus A2 plus A3 plus dot 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 is our answer. Okay. And now for the last question, question 5. This is gonna be such a long video. I think it's over an hour already, sadly. I was hoping it'd be shorter. All the other questions are pretty short, but that last one was like a good 30, 40 minutes long. Alright, question 5. Magnitude and phase of a transfer function. Oh, I didn't like that noise. We must find the magnitude and then the phase. Well, that doesn't seem too bad. It's not that bad. Alright, let me set up the problems down below real quick. Alright, so we have these transfer functions here, and we're given what s can be turned into. So, let's do just that. 2 plus j plus 3. And we have j, stop doing that to me. J minus 1 over j squared plus j plus 2. Alright, we define the magnitude. So we're going to square, how is it done again? I think we square. Alright, so let's do part A first. This is A and B. We're going to, okay, so for this problem, to find the magnitude, we need to grab the magnitude of what's on the denominator. And we need, our main goal is really to get rid of the j's up top as well. And we'll do a few tricks to figure that out. So for this first one, we see that 2 is fine. There's no j's up top. But we got j plus 3. Well, next to that j is a 1, so it would be 1 squared plus 3 squared, square rooted, be 2 over root 10 is equal to the magnitude of whatever. And then let's find the phasor. The phasor for that. It's going to be 0 minus whatever. Because the angle up top is 0. Because it's only a real part. So it's cosine. So on your graph, 2 on this side, well, that's an angle of 0. And for the bottom, 1 divided by 3, inverse tangent, minus 18.43. So the angle is negative 18.43. Alright, now let's move on to the next one. We can simplify the bottom here. J squared is a negative 1. So j minus 1, j plus 1, because that negative 1 got rid of 1. We'll multiply the top and bottom by the conjugate of the bottom. So we'll have 1 squared plus 1 squared left on the bottom. That'll give us enough to fix the top the way we want it. It's going to be j squared minus j. Then we'll get plus j minus 1. Those will cancel. We'll get negative 1 minus 1, which is negative 2. And we're nice and good on the top. Divided by 1 squared plus 1 squared is just 2. Root 2. Multiply the top and bottom by root 2. To fix it, get negative 2 times root 2 divided by 2. These will cancel. And we got negative root 2. Then our angle is going to be, let's see, it's going to be 1 divided by negative 1. Negative 45. And we got 1 divided by 1. Positive 45. So we'll get negative 90 as our phasor. And that's that. Hold on, I did part B wrong. I need to do it over again. I didn't substitute it in right. Holy lordy. This will be negative 4. This will be 2j minus 2. Then we'll do times 2j plus 2 times 2j plus 2. Then we'll get j squared minus 2j. Let me see. And we'll get plus 4j minus 2. We'll get, this will be negative 4 plus 2j minus 2, which will be 2j minus 6. And on the bottom, we'll have just 4 2 squared plus 2 squared, basically. And we'll be left with 4 plus 4, which is 8. We'll square root that, just because we're grabbing the magnitude. And then we're going to fix the top here. 2j minus 8. We'll do 2j root 8 minus 6 over root 8. And let's see. If we factor out a 1/2 out of everything, watch this maneuver. We'll get 4. This will be negative now since the j squared got squared. divided by 8 minus 36 divided by 8, which is negative 1/2 minus 8, 16, 24, I don't know, 18 over 4. Multiply this by 2, we'll get 2 over 4 minus 18 over 4, which is negative 20 over 4, which is equal to negative 5. I think that's right. And now let's do the phase angle. We're going to take 2 divided by negative 6, inverse tangent of this. Because this is what we're looking for. The 2j minus 6 is where we got that from. Negative 18.43. And that will be our answers for this.